So we're going to add to those notes there. I'm going to skip the example 3 there for right now. You've already done the homework, so you've seen a couple like that, I think. We're going to do one with some trig, and then we have to look at the second derivative test for maximum and minimums. Example 4, we've got f of x is defined from 0 to 2 pi, where f of x equals cosine x minus sine x. We want to know where it's concave up. So, first thing we need to do is take the derivative, f prime of x equals, we will have negative sine x minus cosine x. And then, for concavity, we need to look at the second derivative. So, we're going to take the derivative again. So, derivative of sine x is cosine x, so we'll end up with negative cosine x there. Derivative of cosine x is negative sine x, so that'll give us a plus sine x. Alright, so to find our critical values for that second derivative, we have to set that equal to 0. And then what you're probably going to want to do there is just say sine x equals cosine x. And you have to think of your unit circle here to decide where sine x equals cosine x. So 45 degrees or pi over 4 is one of them. And then over here in the second quadrant, sine and cosine are not equal because they have opposite signs. They're also not equal in the fourth quadrant, but in the third quadrant they are. And that is 5 pi over 4. So on our line here, we'll start at 0. We've got pi over 4, 5 pi over 4, and 2 pi. So this is a derivative where we can't really make the chart because we're not multiplying sine and cosine. We're just adding or subtracting them. So we basically just have to plug numbers in to this. So between 0 and pi over 4, the only value we really have there that we can plug in that we know on the unit circle is pi over 6. So that would be negative cosine of pi over 6 plus sine of pi over 6. And let's see, coordinates there are square root of 3 over 2 and 1/2. So we will have cosine will be negative square root of 3 over 2. And then sine is 1/2. So we don't really know what value that is, but we don't have to. We just need to know whether or not it is positive or negative, and it's going to be negative here. Then we need to check something between pi over 4 and 5 pi over 4, which either pi over 2 or pi are both good ones to use for that. So let's do pi. So we get negative cosine of pi plus sine of pi. And cosine of pi, let's see here, we are at negative 1, 0. So we've got negative, negative 1 plus sine of pi is 0. So we get a positive 1 there. So we'll get a positive in this section. More than likely, we're going to get a negative in this next section, but we still want to test just to be sure. The easiest thing to check there is 3 pi over 2. So f double prime of 3 pi over 2 is going to be negative cosine of 3 pi over 2 plus sine of 3 pi over 2. And the coordinates here are 0, negative 1. So cosine is 0. Sine of 3 pi over 2 is negative 1. So we get plus negative 1, which is going to give us a negative there. So this question asks us where this function is concave up. So when we look at our second derivative tells us here that that first derivative here would be decreasing, increasing, and decreasing here, which tells us that the original function would be concave down, up, and down. There. So, because the second derivative is positive, we know f of x is concave up between pi over 4 and pi over 4. So, since f double prime of x is greater than 0 on pi over 4, so 5 pi over 4, f of x is concave up on that interval. Okay, questions on that? Alright, so the trig stuff is the same, except for they will almost always limit it to a region to look at, because if not, this goes on forever and it would be difficult to answer. And you just have to think about that unit circle for these. So, let's see. Let's do, I don't want to run out of time. Let's do number 5. We're probably going to skip number 6. We might come back to it if we get time. So we are looking for all the points of inflection for natural log of the square root of x squared plus 4. The first thing we need to check here is to see if we have any limitations on our domain, because we have a square root here. We also have a natural log. So x squared plus 4 has to be greater than 0. But if you solve that, x squared is greater than negative 4, you square root both sides, you get an imaginary number anyway, right? And if you think of what you've got there, x squared is positive, you add 4 to it, that's positive. So it can't be 0 and it can't be negative. So you do not have any domain restrictions for this. So you can work the problem without having to worry about those. So we are going to take our first derivative. What I would probably do before I do that is it will be a little bit easier to do if we, instead of having natural log of square root of x squared plus 4, that square root is like a 1/2 power. We can pull that 1/2 power out front. So 1/2 natural log of x squared plus 4. And now that 1/2 is a coefficient, so we don't have to mess with it. So when we take our first derivative, we will have just the 1/2 stays out front, and then we'll have 1 over x squared plus 4 times the derivative of x squared plus 4, which is 2x. The 2 in that, with that 2x and the 2 in the denominator of the 1/2, those are going to cancel, so we're just going to get x over x squared plus 4. So that is our first derivative. Now we have to take the second if we're looking for points of inflection. So the second derivative, what rule do we have to use there? Quotient. So we'll have x squared plus 4 times 1 minus x times 2x all over x squared plus 4 squared. And we want to simplify this, so that'll be x squared plus 4 minus 2x squared over x squared plus 4 squared. And that simplifies to 4 minus x squared over x squared plus 4 squared. I may would go ahead and go one more step here and make this 2 plus x, 2 minus x. It will make your chart easier to make at least. Are we okay here? Okay, so we want to set numerator and denominator equal to 0 to get our critical values for that second derivative. When we do that, in the numerator, what will we get? Negative 2 and 2. In the denominator?
You'll end up getting
an imaginary number, because x squared plus 4 is always positive, right? And then you just square it, and it makes it still always positive, right? So we do not get any critical values from the denominator here, but in the top we get x equals 2 and x equals negative 2. So negative 2, 2. So we'll have 2 plus x, 2 minus x. I'm going to write x squared plus 4 squared, but we just decided that is always positive, so fill those in. If you left it off, it wouldn't hurt, but it's not a bad idea. Just always put it there so you're not in the habit of leaving something off that might affect it.
Wait, with negative infinities, square root be positive?
I don't know about that.
Well, it's negative infinity, negative infinity, that makes it positive.
I don't know. It could be indeterminate, but it could be positive infinity. I'm thinking positive infinity, but I'm not certain. I have to look it up. Because I know that like 0 times infinity is an indeterminate. It's not 0, I don't think. Or maybe I'm thinking infinity over infinity, which seems like it should be 1. Right? That is indeterminate. I know that when you start throwing infinities in, things get crazy. So if we plug in like a negative 3 here, we get a negative, and then let's see, 0 would give us positive and positive. If we plug in like a negative 3 here, we'll actually get a positive. A 0 would be a positive, and then we'll get a negative here. So we end up with negative, positive, negative for our final line here that we're going to use. Yeah. Be careful, because like normally it starts with negatives and changes to positives. But on 2 minus x, yeah, on 2 minus x it does not. So we need to know points of inflection for this. So points of inflection are places where our second derivative changes from positive to negative or negative to positive. So we would say f double prime of x has points of, let's see, did it just ask for x coordinates? Oh, of inflection. This one did not just ask for x coordinates, and I've probably not done you justice by not making you find those y coordinates very much. It's just so much work that a lot of times if we can get the x's, I feel like we're good. What would we do to find the y coordinates that go with negative 2 and positive 2? Original. So let's do that. So f of negative 2. We're plugging our x values here. A lot of them I've just asked you for the x coordinates, but this one says find the points of inflection. It doesn't say just the x coordinates, so we need both coordinates. So we're going to have natural log of the square root of 8, which they're probably going to do this with. Let me show you this, just in case this is multiple choice. If it's free response, leave it like that. Don't mess with it. But that 1/2 can come out front. Right? They also might do this. 8. Can we write that using a power?
2 to the third.
2 to the third. So then what could we do?
Move the 3 off front to
3 halves. Natural log of 2. If it's free response, don't do that. Leave it right here for free response. But if it's multiple choice, sometimes they do crazy things like that, and you don't know how they possibly got that answer, but that's what you would do here. If we do f of 2, is anything going to change? Right, because squaring that negative 2 made it positive, so you're going to get the same thing. So 3 halves natural log of 2. So we have points of inflection at negative 2, 3 halves natural log of 2, and positive 2, 3 halves natural log of 2. And again, it's fine to leave it natural log squared root of 8 on the true response. Because the good thing about points of inflection is you don't have to say them differently, like maximums and minimums you have to say separately. Here, we just need to say the sign of the second derivative.
Wait, if we write, is it just f double prime of x has points of inflection?
Oh, thank you. I noticed that just a second ago. I was going to wait a minute to see if you caught it. But this is wrong right here. F double prime does not have points of inflection, right? F double prime is what we use to talk about the original. So I should have right here said f of x. Joe caught it before I even had a chance to ask that. I recognized it just a second ago. But so that should say f of x has points of inflection at negative 2, 3 halves natural log of 2, and 2, 3 halves natural log of 2, because the sign of the second derivative changes at x equals negative 2 and x equals 2. And again, you can word that different ways. You can call it f double prime of x. But you must talk about that second derivative. All right, questions? All right, we are going to skip example 7 because I'm afraid we're going to run out of time, and I want to make sure we get to the second derivative test. So we'll come back to it if we get time. Second derivative test is another way that we can talk about maximums or minimums. Okay, it's not. It is not a way to talk about the points of inflection or concavity. So far, if I asked you to find a maximum or a minimum, you took the first derivative, you found your critical points, you did a sign line, anywhere that it switched from positive to negative or negative to positive gave you those extrema points, right? So that is the first derivative test. And honestly, I usually use the first derivative test for almost every maximum or minimum problem. I don't use the second derivative test often. However, it is possible for them to give you a question where you have to use the second derivative test. And there are a few instances where the second derivative test is a little bit easier. Okay? So, the way the second derivative test works is we know that, first of all, our relative maximum or minimum points can only happen at the critical points of the original problem, of the derivative, I mean. All right, so the critical points come from the derivative equaling 0. All right, so if the second derivative is positive, then that tells us that the graph is concave up there. So if we have a first derivative that's 0, that's going to tell us we have a minimum point, right? Because if it's concave up, it can't have a maximum point. It has to have a minimum point. If we find that the second derivative is negative, that tells us that the graph is concave down at that point. So for it to be concave down, that means you'd have to have a maximum point, right? Sometimes I get those mixed up because concave up sounds like high, which sounds like maximum, right? But it's actually the opposite. Concave up is a minimum. So be careful. I always draw myself a little picture there to remind myself of what that is. If the second derivative equals 0, the test fails, and you've got to use the first derivative test anyway. Like I said, I usually use the first derivative test. But there are are a few cases where it might be easier to do that second derivative test, and sometimes they ask you questions where you have to use the second derivative test. So let's look at example 4. It says, find the relative extrema of f of x equals x squared minus 6x plus 7 using the second derivative test. So for second derivative test, first we're going to find the first derivative, which will be 2x minus 6. Now, we need the critical points for this. That equals 0, right? So 2x equals 6 and x equals 3. So that's our critical value. Okay? So then, rather than doing a sign line, which we could do and would give us the right answer, we're going to take the second derivative. And second derivative is just 2. Okay? So the second derivative is positive, meaning that our graph is concave up, which means that x equals 3 must be a minimum point there. So the way that we explain this on these, we're going to say, since f prime of 3 equals 0, and f double prime of 3 is greater than 0. So, and if you want to think about using more words, since the first derivative equals 0, since you have a critical point there, and the second derivative is positive, f of x has a minimum point at x equals 3. And actually this one did not just ask us for x values either, it asked for the relative extrema. So we probably should find f of 3, which would be 3 squared minus 6 times 3 plus 7, so 9 minus 15 plus 7, negative 9 plus 7 plus negative 2. So the relative, oh, and we should say relative minimum point. The relative minimum is 3, negative 2. And I could have said that all together. I could have said the f of x has a relative minimum point at 3, negative 2 because f prime of 3 equals 0 and f double prime of 3 is greater than 0. So whenever the concept of this usually students don't struggle with too much. It's explaining on these. So you must tell us that the first derivative at that point equals 0. So not f prime of x, or I guess you could say at x equals 3, f prime of x equals 0. But it's easiest just to say f prime of 3 equals 0. And then you're going to that's the first part. And you have to tell whether the second derivative is positive or negative. If you want, you can add in here, which means f of x is concave up. Sometimes I do that because it helps my thought process of understanding why it's a minimum, but that would be optional there. Okay, questions? All right, here's our next one. All right, so relative extrema for this problem, And I didn't specifically say it here, but I want us to use that second derivative test because that's what we're working on here. So f prime of x would equal 6x squared minus 5x minus 4. And then I'm going to go ahead and set that equal to 0, and hopefully that will factor. Let's see. Does it factor? Might need a 6. Give you 5 there. It's going to be a -4 and a +1. That'll work on it. You'll get -8x and a +3x.
Yeah.
-5x, yeah. So our critical values here are going to be x equals 4/3 and x equals -1/2. So if we were wanting to do the first derivative test, at this point we'd make our sign line. But if we're using the second derivative test, we'll take the second derivative, so we'll get 12x minus 5. And then basically we just test our 2 points to see if they're positive or negative. So f double prime of 4/3 would be 12 times 4/3 minus 5. I don't even really care what that is. I know 4/3 is bigger than 1, so that's going to be bigger than 5, right? So this is positive. And then f double prime of -1/2 is going to be 12 times -1/2 minus 5. And that's going to turn that to a negative. Minus a negative will give us a negative there. And let's go ahead and find the x values. I'm going to add that into this problem. Because plugging 4/3 and -1/2 back into your original equation here, it's possible it's not that bad, not terrible, but it's time consuming, so I don't want to spend a lot of time working on that right now. So let's just use our x values for this one. So let's do -1/2 first. At -1/2, do I have a maximum or a minimum? I have a maximum because this negative right here, that second derivative being negative, tells us that it's concave down. Right? And if the graph is concave down at that point, you have a maximum. And then up here, this tells us it's concave up. Concave up means that we have a relative minimum. So we must explain it. So f of x has a relative minimum at x equals 4/3 because f prime of 4/3 equals 0 and f prime, double prime of 4/3 is greater than 0. And then f of x has a relative maximum at x equals -1/2 because f prime of -1/2 equals 0 and f double prime of -1/2 less than 0. questions there? All right, so let's see. Rather than doing this, I'm thinking about going back in. This is really more of the same. Do you guys need to see another one of those? Let's go back and do that example 7 that we skipped. That one with the E. Okay, so we want to know where this is concave down. So let's do f prime of x. When we take the derivative of, I actually might change this first. This is e to the negative 2x to the negative 1 there. Because negative 2 over x, when we have negative 2 over x, we can move that to the top and have negative 2x to negative 1. So the derivative of e to the negative 2x to the negative 1 is e to the negative 2x to the negative 1. But then we must multiply by the derivative of the exponent, which is going to give us positive 2x to the negative 2. So that is going to give us e to the negative 2x to the negative 1 over, let's put the 2 out here, x squared. Or you don't necessarily have to do that. It just depends on whether you want to do a product rule or a quotient rule for this. I think I'll go with a quotient rule. There's a lot of different things you can do with those negative exponents. So when we look at the second derivative, we're going to have x squared times the derivative of 2e to the negative 2x to the negative 1, so that's 2e to the negative 2x to the negative 1, times the derivative of negative 2x to the negative 1, which is positive 2x to the negative 2, minus 2e to the negative 2x to the negative 1, times the derivative of x squared, which is 2x, all over x squared squared, which will give us x to the 4th. First derivative is not too bad. The second derivative starts to get a little bit crazy. So let's clean this up a little bit. I'm probably going to want to factor out that e to the negative 2x to the negative 1. So we'll have 4. What happens when we have an x squared and an x to the negative 2? They cancel each other out there. So we're just going to have 4e to the negative 2x to the negative 1. Minus, and here we'll get 4x e to the negative 2x to the negative 1, all over x to the 4th. And it will be easier to do this problem if you factor out that e to the negative 2x to the negative 1. And I'm going to go ahead and take a 4 with it. 4e to the negative 2x to the negative 1 times 1 minus x, all over x to the 4th. And then for plugging, or do I even care? I don't think we even care. If we needed to plug in numbers, it does make it a little bit easier to go ahead and make this back e to the negative 2x to the negative 1. That is e to the negative 2 over x. And then, since you have e to the negative 2 over x, you can send it back down to the bottom. But let's just leave it because it really doesn't matter that much. We'll see whenever we do this. Because e to the negative 2x to the negative 1, is it ever 0?
No.
Is it ever negative?
No.
No, it's always positive. So it's not going to factor into our sign line very much, and it's not going to be a critical value. So rather than try to work with it some, let's just leave it like it is. So the critical values are going to come from this 1 minus x, which will give us x equals 1, and then the denominator, x equals 0. All right. So on our sign line, we will have 0 and we will have 1. And I've got 4e to the negative 2x to the negative 1. I've got 1 minus x, and I've got x to the 4th. And I've not left room for my answer there very much. Let's see, f double prime of x. So, 4e to the negative 2x to the negative 1, always positive. All right, x to the 4th, always positive. And then we've got 1 minus x. So if I plug in a number like negative 1, I'll get a positive. Number between 0 and 1, I'll still get a positive. But for anything above 1, I'll get a negative. So for this, I will get positive, positive, negative. Okay. And it's asking for where this is concave down. So we would say f of x is concave down on 1 to infinity, because f prime of x is less than, f double prime of x is less than 0 on that interval. So with those e's, a lot of times, you've got to make sure that you do the derivative right. But once you actually start making your sign line, the e does not usually give you critical points, and it also does not give you a sign change because it's always positive. So when it comes to that point, it's always positive.
So on that, like little graph, it was positive, negative, and switch.
Right. Occasionally that will happen.
Okay.
What may happen here, see the second derivative is 0 at that point.
Yeah.
So what you probably have is like it almost switches, but not quite. You know, like you have like a dip there, but
0. Wait, so that was the second derivative of 0?
Second derivative is 0. Yes. Okay. So the assignment that you guys will do that goes with this is page 242, and you guys are going to do 35 through 49 odd. And these are second derivative test problems. All of these are second derivative test problems. So you will use that where you have to find the first derivative and then find whether or not the second derivative is positive